Yes, sir.
I have a question. How do we purchase the homework? Because it says to like do it on Maple Cloud, but like there's really a clear place to put it there.
No, I just wanted someone to try to upload to the link. I mean, like I said, I'm not sure how well it would work because I haven't uploaded an image to that shared folder before. Has anyone uploaded a file there before? I'm not going to talk about it now at 9:30. So just if someone tries and it doesn't work, I can just change the format of the link and you can upload to the OneDrive. So just kind of a simple email would be easy and just save us time. So again, if it doesn't work, it's just let me know quickly and I can change the link to a OneDrive link. Maybe that option is just for a Maple file. So first person to try, if it doesn't work, just shoot me an email and within a minute I can change the link. So. Verify attendance so we can get started. Perfect. See Carlos Aguilar, Alex Bernard. Aaron Bradshaw, Brett Buckner, Alicia Hernandez. Is Alicia there, Austin? Austin, can you hear me?
Yeah, I can hear you.
Is Alicia there?
No.
Luke Childers, Leo Cruz, is Leo there? Okay, I'll follow up. Haley Evans, Aiden, Maria, Kana, Blake, Spencer, Jackie, not yours yet. Austin, you're there. Binov, Sean, Ethan, Alicia, Ernesto.
Okay, I'm not getting any video or any sound.
Good. Austin, let Professor Evans know that we can hear it clearly.
I think I did that.
You want to mute her?
That's right.
And is Manny there, Austin?
Yeah, he's right here. He's clicking his Zoom right now.
Okay, so I'll check him soon. All right, excellent. Let me share my screen. As I was saying earlier, just for the assignment that's due today, once you've worked out your solution, just attempt, the first person to attempt to upload, if there are any issues, just let me know and I can change the link to OneDrive link. I was trying to keep everything in Maple Cloud. So just feel free to work through that at some point. All you need to do is just take an image of your work and upload it to the shared folder. But again, I've never done it before using Maple Cloud for an image or in a Word document. I've only done that for Maple files. Just let me know if it works fine for you. Good. Again, do keep up with your assignments, because they'll continue to increase and more consistent week by week. So I'll have the presentation problems for next week. I didn't want to do any ones this week, but I'll have them available by the end of the day today. And so you can start working on those. I'll continue to increase the use of Maple. So make sure you can access that through machines here for JCC students, as well as using the Maple virtualization, and that's also accessible to students at Samson Community College as well. All right, let's continue where we left off. Oh, yes, Alex.
How do you upload something to Maple Cloud? Because it might be a place you want us to share it, but there's really any upload anything.
Well, just send me a screenshot. I'm not going to go through that in class. As I said, if it doesn't work, I can change it. If you just send me a screenshot of what you're seeing, then I'll just change the format if it's not given an option to upload a file. I think last class we ended with using the arc length parameterization of a curve. Let me go back to the example. I think it was this example on slide number 7. And that was, finding the, is this correcting the tangent vector? Oh, we went beyond this point. Give me just a second. I think we ended by looking at the arc length parameterization of a curve, correct? In curvature in that sense. So let me just slide on. Good. So it was slide 16. I know we got to the end of this section. So just quickly going over this exercise, we're able to reparameterize this particular curve by expressing it in terms of the arc length parameter. By definition, the arc length parameter S is true when the magnitude of r prime t is in fact 1. And well, t would be expressed in S in that sense. So what we did in this particular example, we re-expressed the curve in terms of S, and we found that if it's practical to write the curve in terms of its arc length parameter, then curvature can be easily determined by taking the second derivative with respect to S. So the idea is that it's not always practical to do this. If not, what's next? So we'll actually engage in a couple of intense proofs today and look at some alternative forms to find curvature as we continue to study the vector value functions. In your text, well, let me give you a page number so you can follow along. It should be, this is 2.3. On page 59, if we'll pick up from here, continue, I'll make this a bit larger for you. Good. So let's take a look at that particular proof. So I rewrote the proof just using some more common languages and added some additional comments. So here to say, let h of t be a smooth parameterized curve and let r of s be its arc length re-parameterization. Clear? Then if that's true, then h of t would be equal to r of s of t. Remember, the re-parameterization just takes a look at the, taking the antiderivative from 0 to t. So just replace a with 0 to t of r magnitude of r prime t dt. So this is really rewriting it as a composition of functions. But if we differentiate both sides with respect to t, that would require the chain rule. That implies that d by dt of h of t, keep in mind that h of this derivative is the same as h prime t, which is also velocity. That will require the chain rule on the right-hand side, and that derivative of r of s of t would require the derivative of the inside. That's why I have them highlighted in yellow, which is d by dt of s of t times the derivative of the vector value function expressed as a composition of s of t and r of t. What makes these proofs challenging is for you to instantly distinguish between a vector and a scalar. So often it's best to rewrite these proofs. You get nothing just by looking at it. So at some point in time, I expect you to rework this proof on your own, okay? So do understand that this is a vector, that's a vector, this is a scalar, good? When I take the derivative, the chain rule looks at the derivative of the vector times the derivative of the scalar. Next, we take the magnitude of both sides. If I take the magnitude of a vector, right, that gives me a scalar. Then the magnitude of this product will be the magnitude of the vector times the absolute value of the scalar. This was an elementary concept we established in chapter 11. So the magnitude bar would not be expressed around d by dt of s of t because this is in fact a scalar quantity. So let me make some notes on this for you at this point. So these are things that aren't obvious in the textbook proof. So I want to make sure you're clear on that. That's the scalar quantity, and that's why it's written when we take the magnitude, you just only use the absolute value bar just below. Is that clear? Very good. So I also note that speed is the magnitude of h prime of t, and h prime of t is d by dt of h of t. So it's saying a lot of things multiple different ways. So do make a note that this is speed, which is now a vector scalar. Beautiful. All right. So far, so good? All right. Next, in text note that since ds by dt, which is the rate of change of the particle along the curve with respect to time, speed is greater than 0. This is true because s is increasing based on the actual curve itself. But one thing to note is that if we think about now what does this represent? Let me not tell you everything. What is big T of t? Unit tangent vector, very good, which is d by dt of h of t divided by the magnitude, or you may say r prime t divided by magnitude r prime t. Once again, I've highlighted some terms to show you that d by dt of h of t, that's coming from what's in blue, okay? So I've taken information on the right-hand side, which replaces d by dt of h of t, as well as information here on the right, which replaces magnitude. And then we can express t in this form. What you realize is that this particular proof rewrites big T of t as a composition with s of t. Simple substitution, and the fact that d by dt of s of t is exactly the same as the magnitude of d by dt of s of t. Sorry, the absolute value, apologize. But the absolute value implies it's always positive, right? And we assume that this is also positive, so these actually cancel each other out. That's what your text did. Hence, we're left with d by dt of r of s of t divided by the magnitude, and that implies that t of t with this reparametrization can be expressed as t of s of t. Does it make sense so far? Finally, we differentiate both sides with respect to s using the chain rule. Any questions before I go to the next slide? Give you a chance to copy it. Okay.
This is what we did on Monday, right? Just as a proof.
I'm sorry, what was the question?
This is what we did on Monday, right? Just as a proof.
We're leading to another form of what we did on Monday. So what we did on Monday was, in fact, it was good that you see that relationship. That's great. So what we did on Monday was actually find curvature using the arc length parameter. And I reiterated earlier that it's not always practical to do that. So this proof is leading to something interesting. And we'll look at several today. The final slide for this proof shows the derivative of T of T reparametrized as T of S of T. Again, using the chain rule that implies, let me read this to you, d by dt of T of S of T. Oh, sorry, yes, go ahead. Oh, let me go back here. Here. Oh, very good question. And that's because by definition of the unit tangent vector, it's d by dt of, in this case, the position vector divided by its magnitude. What happens is that this is now written in another form. H of t is now written as r of s of t. So d by dt of r of s of t, or let's just say d by dt of r divided by the magnitude of d by dt of r is in fact t. And the only thing that changes is actually the composition. So it's the composition from t to, in fact, s of t, because these two expressions are in fact similar. The only difference is what's written here. That's an h, then that's an h, correct? And this is r of s of t, and it's r of s of t. Still implies big T of s of t in this case. That make sense? Now, if I take the derivative of the left-hand side, which implies the derivative of the right, I would need the chain rule, which is taking the derivative of s of t, which is d by dt of s of t, and multiplying that by d by dt of t of s of t, hence the chain rule as stated above. So what changes slightly is the fact that d by dt of s of t is in fact the magnitude of h of t. You should have questions. Why is that true? Anyone, feel free to. Remember, as you look, determine what's a scalar, what's a vector. I'll give you another minute. We're doing good with time. Good, which is a scalar. What is d by dt of s of t? But what does that scalar mean? One word. Speed. And on the right, what is this? Also speed. Because d by dt of h of t is in fact h prime of t. And the magnitude of h prime of t or magnitude of r prime of t is in fact speed. Remember, we established that speed is ds by dt because e by dt of s of t is same as ds by dt. That's in fact speed. So we re-expressed speed in terms of this notation because it's convenient to do so. And the reason why it's convenient to do so is going to allow us to solve for d by dt of t of s of t which gives us d by dt of t over the magnitude of d by dt of h of t. I can express in some more common terms is in fact saying t prime of t divided by v of t. What is v of t?
It's the speed.
Okay, it's not velocity, right? Oh yeah. It didn't say it was simple. I said this would probably be one of the most intense chapters for you as we move on. So because of how inconsistent the language can be. So the arrow is not above, it's not a vector, but this is in fact speed. So what you want to do is actually decode in this chapter. So it's best if we just make an assumption. One, let's assume that we're now working with a vector value function. Let's just say r of t. I'm just going to write here an assumption, which is fair. Let's assume that's the function we're working with. Then what must be true is that d by dt of t of s of t is equal to t prime of t, that doesn't change, over the what is it, magnitude d by d. I don't have to write the d by dt anymore. It's just magnitude of r prime of t. I didn't leave anything off. Let me see. There we go. So it's essentially looking at page 60 of your proof. And let me put things in perspective for you. So I'm forgetting t prime t. So put things in perspective, I'm gonna jump to where we left off last class, then we can move forward. So last class we, where's my formula? Yes. Curvature, right? Do you recall this curvature formula in terms of S? Good. And it said the fact is magnitude of d by ds of t of s is in fact the magnitude of r2 prime of s. And how did we show this? Here, right? Remember, t of s was said is r prime of s divided by its magnitude. And we established that when working with the arc length parameter, the magnitude of r prime of s is always equal to 1. Good. So t of s is in fact r prime of s. So d by ds of t of s implies d by ds of r prime of s, which is r2 prime of s. Let's take a look at this expression, d by ds of t of s. Good. And then at the end of our proof, we end up with d by dt of t of s of t. The only difference is we actually reparameterize in terms of s of t, which implies that this left-hand side is curvature. You've just proved a curvature formula in terms of t. It's okay. What the curvature formula implies is that k of t can be determined using t prime of t divided by the magnitude of r prime of t. It's the same thing as your text. Let me just toggle back and forth. the text now, this is theorem 3 that says K of t is d by dt of t divided by v of t. So let me write that for you. So in your text, curvature is d by dt of, and use the hat, or it doesn't matter, of t divided by v of t. Was there a magnitude? I can't recall if there's a magnitude there. It's actually a magnitude that applies here. And I think I made a step in the proof that led to this, but the curvature would then be the magnitude of d by dt of, actually the magnitude of that divided by speed. So this should have been a magnitude here as well. I think I made a step, but it's fine. You can reintroduce that. So there's an alternative step that leads to this actual magnitude, but the idea is that the curvature now can be determined in terms of t, which is really a breakthrough point for us, because now we have a formula for finding curvature if it's not practical to express the curve in terms of its arc length parameter. So I said, just an easy way of writing it is nothing more than writing the magnitude of t prime of t divided by the magnitude of r prime of t. I'll tell you right now, the issue with this particular formula is the derivative of the unit tangent vector. As much as possible in this course, you want to avoid that. So I'll do a single example that requires that derivative. Okay? And that's, well, this is actual formula from your text. So if you take a look at exercise 16, that says find the curvature k of t for this particular vector value function on the given interval. Just by definition, k of t would be the magnitude, because curvature is a scalar. So the magnitude of t prime of t divided by the magnitude of r prime of t. I won't keep writing v a lot. Just remember that this implies v of t, which is still speed. So step one, let's find the first derivative, r prime of t. What's my first derivative? One. That's good. And then what's one? Yeah. Mm-hmm. So what should this be? T. Well, it's 3 to the t to the, so we multiply by 3 halves, right? And then it would be 3 halves minus 1. And that would, minus 1 would give us? Okay. 1 over 2, right? Good. No, I heard t, so I was at first. Yes, absolutely. So now that we have r prime of t, we need to find t of t before we find this derivative, correct? By definition, t of t is r prime vector, r prime of t divided by its magnitude. We've already determined r prime of t. And the magnitude of that vector would give us what? All right, 2 plus t. So 1 squared is 1, 1 squared is 1, t to the 1/2 squared is just t. So here we are. Now, let me rewrite t so we can effectively find its derivative. I assure you this is the only time I will take the derivative of big T of t. You may choose to do that multiple times, and that's entirely on you. So that's 1 over root of 2 plus t. This is going to be radical t divided by radical 2 plus t, comma, 1 over root 2 plus t. Now let's find its derivative. From the last homework set, I'm sure you've had enough practice with that rigorous derivative worksheet, right? Because the expectation is that you're doing the homework. So I'm going to assume that you're smart enough to do the homework. So the derivative of this doesn't require the quotient rule. I'm going to use the chain rule, bring this to the top, make it to negative 1/2 power, multiply by negative 1/2. Good? So negative 1/2. Using the chain rule, the derivative of that inside is in fact 1. And I'm going to minus 1, which makes it negative 3/2. So at least show that step. Fair enough? I would recommend we rewrite this expression just for the purpose of the derivative as the root of t over 2 plus t. And we can apply the chain rule and quotient rule in 1. So using the chain rule, I'd bring down 1/2. Good. This is just all this expression to 1/2 written t, I'm running out of room, 2 plus t, the negative multiplied by the derivative of the inside, which requires the, is this correct so far? And multiplied by the derivative of the inside, which is the basic quotient rule. I'm just wrap this around here for you. So that would be d, the denominator, multiplied by the derivative of the numerator, which is 1, minus the numerator multiplied by the derivative of the denominator, which is 1, divided by the denominator squared. And my third term, which is similar to my first term, I'll rewrite this a bit better, would be the same as this, just negative 1/2, 2 plus t to the negative 3/2 plus my vector. So I'm going to clean up t prime of t for you. So negative powers, let's rewrite this. This is going to be the square root of t, 2 plus t to the third. Yes, go ahead. Yes, I did say squared and squared, didn't I? Thank you so much. So for this first term, that's going to be a negative term, 1 divided by twice the square root of 2 plus t cubed. So express this in radical form. I don't want a lot of I won't combine a whole lot here, but there are a couple of things that are happening. So let me write this out for you before skipping too many steps. So this is a 1/2, and that stays the same. T over 2 plus t to negative 1/2. In fact, it's just a matter of taking the reciprocal of that expression. 2 plus t over t to the 1/2. You know that? Negative power can do that. What does this numerator become? This, good, so multiplied by 2 over 2 plus t, not 2t, squared. comma, and then my third term is the same as my first here. Still wrapping around a bit. So it's negative 2 radical 2 plus t to the third. Close. I wanted to show an additional step for the middle because we need to clean this up a bit before we take its magnitude, okay? So once more, a simpler version of t prime of t would of course be what we have written there, negative 1 divided by twice root of 2 plus t to the third, comma. So you realize that the 2 in the denominator cancels the 2 in the numerator, correct? This is 2 plus t to the 1/2, which reduces this power by 1/2. And this remains root of t. So that would be root of t. And then this would be, in fact, 2 plus t to the 3/2, which is exactly what's here. 2 plus t. And numerator of 1, comma, negative 1. Good. Beautiful. And that's t prime of t. So 5 minutes ago, what is it you want to avoid as much as possible? The only way to avoid that is the knowledge of vectors that I hope you bring forward or you brought forward from the previous chapter. So we'll look at that soon. But I'd like to give you options. You don't want to know vectors, feel free to take as many derivatives as you like. But we're not done. Let's take the magnitude. Still finding curvature, right? We're going to revisit this problem with a vector approach. So take the magnitude of t prime of t, which is the magnitude of this vector. Shouldn't be that bad now. Which is the square root of these components squared. Good. So that will be a positive 1 divided by 4. The radical squares goes away, so you'll have similar denominators, I suppose. What is this? 2 plus t to the third, good, plus 1 over t, 2 plus t to the third, plus 1 over 4, 2 plus t to the third. Good? How do we add these fractions or rational expressions? It's fairly simple. Let me highlight what's consistent across, right? And what's different is 4 and t. So I'm missing a t on this side, so multiply by t in the top, t in the bottom, right? Okay. Here I just need a 4 in the top, 4 at the bottom. Here I need a t at the top, t at the bottom. So my common denominator is just 4 times t, 2 plus t to the third. And my numerator would be the sum of t, 4, and t, which is 2t plus 4. That would be 2t plus 4 under my radical, good, divided by 4t, 2 plus t to the third, also beneath the radical sign. I just separated them. Yeah. Who knows? You don't really have to. At this point, I don't want to keep simplifying. It's fine. Should I simplify a bit more? Yeah, you can factor 2, which leaves you 2, root 2 times root of t plus 2, which reduces, kind of one of these. So one other simplification of this just gives you root 2 divided by 2 root t Is it cubed? Yep. One or the other. If you don't get this, this is algebra. I'm not going to get too much into that. So you can actually simplify and get to this point. Bottom line is we want to find curvature. And curvature in terms of t for this expression would take one of these expressions. Let's just choose the top, assuming that not everyone sees this at this point. And that would be root of 2t plus 4 divided by root of 4, let's make that my t, 2 plus t to the third. That's just the magnitude of t prime of t. And we divide that by speed. What is speed? Oh, here it is, the magnitude of r prime t, correct? Which is the root of 2 plus t. Good. Using this formula, it would lead to a very simple answer because the root of 2 plus t multiplies root of 2 plus t, which is just 2 plus t. And you're tired of hearing 2 plus t and t and 2s. But that's just the fact. So I'll write the final answer in a more simplified form, but you could stop here and exercise your algebraic skills. But at this point, a simpler form of k of t, the curvature in terms of t, would be, let's just make this 1 over root 2, which is just root 2t. Let's group those together. And when we multiply these two radicals, it would be 2 plus t. Yes? This one?
Yeah, I think it should be.
3 halves.
Yeah.
This was a radical. It's actually 3 halves minus 1 half,
Yes.
which is just 1. Absolutely, it makes it easier. Absolutely. Thank you, thank you. This 3 halves minus 1 half is 1, not 1 half. Did the little. So that should just be 2 plus t. Thank you, Ethan. What would we do without Ethan? Of course, the rest of you saw that. So this would actually be 2 plus t to the 3 halves. So you brought back the radical, I guess.
The weights, you can just kept it in that form,
Mhm.
and you can see that the square root of 2t plus 4 divided by the square root.
Yeah. Either way, it's fine. I don't want to get hung up in the algebra, but I apologize for overlooking that. But the reality is either form is fine. Ultimately, we want to be able to express curvature in terms of t. But does everyone see what happened here? Because the reality, this was in fact 2 times the root of. This was in fact root 2, factor root 2. And that's where this came from. And this, what's left is the root of t plus 2. Good. And what's in the denominator here is in fact root of 4, which is 2. Root of t is root of t. And this is the root of 2 plus t cubed, which is 2 plus t to the 3 halves. And this is t plus 2 to the 1 half. And the commutative property of addition says they're the same. Hence, we just take 1 half and subtract it from 3 halves, which is just 1. And that led to that first problem. All right, and that's the curvature. That's a lot of time for one problem. Good. If you use this approach on my examination, you won't finish it. I'll just be honest with you. And the exams are not this simple, because this was actually simple. Okay, let's change modes. Are you ready? So as I said, it's not always practical to express the vector value function in terms of its arc length parameter. If it is practical, then curvature can be computed just using that form, okay? Curvature is just the magnitude of R2 prime of S. If not, we establish the fact using the proof that curvature can be expressed in terms of t, which is the magnitude of t prime of t divided by speed. If so, curvature would require the derivative of the unit tangent vector. Fair enough. Now, 2.3.3 looks at what's called the unit normal and binormal vectors. So let's see the smooth curve represented by R on open interval I. If the derivative of the unit tangent vector is not 0, then the principal unit normal vector at T is defined as. So now there's another unit vector defined n of T, which is T prime of T divided by its magnitude. So see how messy this can really get? But this is not the approach we're going to use to find n. Just follow along. This is called the principal unit normal vector. The principal unit normal vector is another unit vector, not just any unit vector. It is a unit vector that also points in the direction of concavity, right? Just as acceleration, but this vector is in fact orthogonal to the unit tangent vector. So a number of things to note here. So one, n of T is the derivative of T of T divided by its magnitude. So these computations should be done in Maple, not by hand. I'll be honest with you. Because there's a lot of algebra and derivatives that you already know, and leads to a lot of computational errors that we want to avoid. So one thing to note is that there are infinitely many vectors that are orthogonal to the unit tangent vector. It's a very powerful statement because at this point you only see one, right? Why are there infinitely many vectors n orthogonal to T? Yes, sir. Multiplied by another scalar. Okay, good. And hence you create a set that's parallel to n. Do note that T prime of T is also orthogonal to T because T prime of T points in the same direction as n. Is that clear? Are there any other, any other ways of describing that infinite set? No one else. Samson, Manny. Colin. Can you think of any other ways of defining the infinite set of vectors orthogonal to T, big T, it is? What I'm asking you to do is to take this very static diagram and make it dynamic. You're in space, try to rotate it in your mind somehow and realize that this is not two-dimensional, it's three-dimensional. So can you think of any? Any others? If not, it's okay. Luke. Maria? Anyone? Ethan?
This is the cross product of the position vector and the unit vector.
Oh, that's one. Yes, you could. You could cross the position and unit tangent, and there's a vector orthogonal to it. Absolutely. Yeah, very good. Any other ways? I'm gonna just make a quick sketch in this diagram. I'm gonna draw a disk that's contained in a plane with T as its normal vector. And that disk is centered at this point, which means n points in the direction of a radial line containing that disk. And I can draw infinite radial lines. So there's a disk spinning at that point with the tangent vector projecting along the curve. Space travel is rather complex. How many of you want to study aerospace engineering? Anyone in this class? Samson? So this is really good knowledge you want to bring forward. This is the heart of aerospace engineering. Just want to throw it out there. Also note that if I dot big T in itself, remember if I dot two vectors, it's the magnitude of the vector squared. Good. In this case, T dot T is in fact 1. Fair enough? Also note that T dot R, T prime of T is 0. Why is this the case? Why is T dot T prime T 0? They're orthogonal, good, because T prime T runs along N, right? And with that said, we can certainly state that if I dot T and N, what would that give me?
0 because they're orthogonal.
Good, because T and N are orthogonal. Also note that, again, reiterate, N points towards the concave side of a curve. Good. Thoughts or questions? Good. Page 63 of your text introduces, I won't go through that proof, that would just too much to handle at this point. But I'll just reiterate what I snapped from the actual page. It says when we zoom into a point of a curve, the curve appears to lie in a plane which contains T and N. It says in the next section we'll study this plane, and this plane is called the oscillating plane, which always contains the acceleration vector. Because when the unit normal vector n is defined, it is proportional to the derivative of the unit tangent vector t. So if you find this statement confusing in terms of the proportionality statement, I'm going to go back to this diagram and reiterate what they're saying. Remember we said that n and t, prime t, are in the same direction, right? Which means that these vectors are parallel. And if two vectors are parallel, one is a scalar multiple of the other. Hence your proportionality statement here. What emerges, from the discussion in the text is this actual equation. So this equation above is true in general for an arbitrary smooth curve known as the first Frenet-Serre equation that expresses dt by ds, d by ds of the unit tangent vector in terms of s, the arc length parameter, and that's equal to curvature in terms of s times the unit normal vector in terms of s. Very powerful equation. Check mark there. But as always, we express things in terms of s and express things in terms of t. It also can be shown that the Frenet-Serre equation, another alternative form of it, can be expressed in terms of t, which is k of t, speed, which is v of t, times n of t. We'll do some work with the Frenet-Serre equations at the end of this chapter. You didn't see that, did you? Let me undo. It's awful. Any questions? Okay, we're heading somewhere. So there's a third vector called the binormal vector. So important things to note here. So a lot will be said and we'll get back to some computation soon. It says the vector B, which is equal to T cross N. Are you surprised? So you have T and N, right? They're orthogonal. I mean, we cross those two vectors, it creates another vector called B, the binormal vector. It says it too is a unit vector and is perpendicular to both T and N. The unit vector T, the principal unit normal N, and the binormal B have the initial point at P, and they form a right-handed mutually perpendicular triple of unit vectors known as the trihedral. So again, the three vectors, if you cross T and N to obtain B, they form mutually. So does that ring a bell? Wasn't that a test question? You all had that on versions 1 and 2. Mutually perpendicular vectors. Remember that question where you had three vectors to show they're mutually perpendicular? I said, just continue to dot the corresponding vectors. Yeah, it was leading to this concept. If you don't remember, it's okay, but maybe you want to forget about that exam, some of you. But the idea behind that was that that particular test question was written to lead you to this concept, that these vectors T, N, and B are mutually perpendicular. So they're not just mutually perpendicular, they're in fact mutually perpendicular triple of unit vectors. They're all unit vectors, and they're defined as the trihedral. So earlier the text talks about specific types of planes, and I want you to make a note of this. So if you can see clearly, this is a tangent vector pointing to the left. The normal vector is pointing towards concavity. The plane containing T and N, just by these red dotted lines, is called the oscillating plane. Good.
Just T and N?
Yes. The plane containing T and N is called the oscillating plane. The plane containing N and B is called the normal plane. And the plane containing T and B is called the rectifying plane.
Is the vector B going up, or which way is it going?
Yeah, it's going upwards, and I can reproduce that here. Let me just redraw that for you. So here we have B, and T was pointing that direction. Let me, and it's because of the positioning, so let me rotate this a bit differently. Maybe it's better if I just use that orientation. So this vector was in fact T. This is N. And this was my, sorry, this was N, I apologize. And this is B. So this is my unit tangent vector, my normal vector, the plane containing T and N, called the oscillating plane. That's that plane. The plane containing B and N, that's called my normal plane. And the plane containing T and B is called the rectifying plane. We have oscillating plane, my normal plane, and then this is my rectifying plane. And all these vectors form what are called the Frenet-Serre vectors, the Frenet-Serre equations. Not today, but I'm sure by part of class of Friday, we'll actually find the equation of the oscillating plane, because we're studying finding the equation of a plane, right? And we do know that the vector B, the binomial, is one of its significance. It allows us to find the equation of that oscillating plane. In fact, we can find the equation of all these planes and reconstruct this. Yes, Marie?
So B and, or vector B and vector N are not opposite of each other, they're at an angle?
Yes, they're orthogonal to each other. It was just, it's positioned weird on this screen. I'll show you how to reproduce this. The text talks about a procedure in Maple to reproduce this as well, but we'll spend much more time on this in Maple just to add that dynamic component of it. I just want you to understand the concepts, be able to address the problems related to this, especially using a vector approach.
It's more like an XYZ.
It's very much so, because the XYZ coordinate system, once you make the unit vectors I, J, and K, that was in fact your first introduction to the Frenet array vectors. 0, 0, 1, 1, 0, 0, 0, 1, 0. Does that ring a bell? So,
That's what RJ and K.
yeah. I is a vector which is 1, 0, 0. J is a vector, and K is a vector. They're all unit vectors, and they're all mutually orthogonal unit vectors are, in fact, the Frenet array vectors formed tetrahedral. You were introduced to it before. I'm just making sense of what you've already done. Honestly, it's nothing new.
Except now instead of it being at the origin, I'll bring up.
Exactly, because we draw too many assumptions in mathematics. It could be anywhere. And if that's the case, this is what it forms. Welcome to Calc 3, by the way. So, as I said, I won't use Maple, but in Maple, we'll be able to reproduce this easily. So you can actually see the Frenet array vectors. As you said, Blake, it can be anywhere. So here's this segue to what you just said. The vectors can be anywhere on the curve. You'll be able to reproduce this easily using Maple. There's nothing difficult about doing this in Maple. I want you to understand conceptually what it is we're talking about, though. So just for example, let's work through this by hand. We're going to find the derivative of t in this case, and I'll tell you right now it's going to be very simple, and I'll give you the reason why right away, because of these components are trigonometric in nature, and when you find the derivative and square them, it forms the Pythagorean identity, and it's just so easy that I will never give you on your exam. Just want to make sure it's clear. Yeah. But let's just work through it anyway. So let's find t. This is r. I think it's only fair to tell you. So the derivative is going to be 9 cosine of t, 4 negative 9 sine of t. And then if I take the magnitude of r prime of t, I hope you're okay if I skip a couple of steps. That's 81 cosine squared, 81 sine squared. That's just going to be 81 plus 16. What is that number? I'm not going to add it because I'm not going to make a mistake. Okay. So you said it, not me. Before Ethan calls me out again. So it's okay. No. I think I'm the bad guy because I'm throwing it back in someone else. No. You're the good guy. Did I make a mistake again? Oh my goodness.
Me whenever I do math.
So is it 81 plus no 81, you factor 81, so it's only 81 once. So it'd be 81 factored cosine squared t plus sine squared t, which should just be 81, yes. Yeah, good. And hence that is, this is in fact, if we divide these two, that will give us our big T of t. That would be in fact 9 divided by root 97 cosine t, comma 4 divided by, that's a 4 by the way, divided by root 97. Do you follow along? Comma negative 9 divided by root 97 sine t. Fair enough? And if this is big T of t, I mean, you want to find this derivative because it doesn't involve anything complex. Again, this is going to be negative 9 divided by root 97. Sine of t, that's going to be 0. This is going to be negative 9 divided by root 97. Cosine of t. Fair enough? Taking the magnitude of t prime of t, that's going to be the square root of these components squared. So what is this magnitude going to give us?
Root 81 over 97.
Which is in fact 9 over root 97. One thing to know, when it works out this smoothly, we could have re-expressed the curve in terms of its arc length parameter. So these are cases when it's practical, but it wasn't necessary here. Now n of t is just dividing each of these ratios, which gives us negative sine of t, 0, and cosine of t. Negative, yes. So keep in mind, because of the order in which it's written, t prime divided by its magnitude just divides these components by what we obtained here. Fair enough? And now to find b, the binomial vector, b of t, that would be t cross n. Order is important. Thoughts or questions? And find that cross product. Yes, Ethan.
Can you briefly explain how you got the NFT?
Yes. N of t is t prime divided by its magnitude. So I took the answer here and divided each of these components by that result. So it would be negative 9 over root 7 sine t divided by 9 over root 97, and it just cancels out. Thanks for asking. Doing t cross n, remember the I, j, k components? And expansion by minors. T, where's t again? T is this component, right? I'm gonna factor 1 over root 97. Because we can do that. I'm left with 9 cosine t, 4, and negative 9 sine t. Is that correct? For t, yeah. 9 cosine t, 4, negative 9 sine t. And I'll factor the negative sign for n. I just want to deal with negatives. And that's sine of t, 0, and cosine of t. And that's negative 1 over root 97. And now I can find my cross product. So that's going to be 4 cosine t, correct? For I component. For j component, it's going to be 9 cosine t, sorry, 9 cosine squared t plus 9, it's just beautiful. Let's just love it. So that should be negative 1. That's my guess. Please verify. Bless you. If that's a sneeze. Is that correct?
That should be 9. Isn't the negative for k should be positive 9 sine of t? Or no, this is t, not derivative t. I'm looking at the wrong thing.
Negative or negative 9?
Yeah.
Negative 9 or positive 9? Remember, plus, minus, plus. Negative 9. And the final term would be minus 4 sine t. Is that correct? Fair enough? All right, good. So the binomial vector b of t, I'll just bring this back into the expression. Be negative 4 over root 97 cosine t 9, positive 9 over root 97, and 4, positive 4 sine t over root 97. If you're unsure if it's correct, you can just dot any corresponding vectors, and the dot product must give you 0. You can test that the magnitude is in fact 1 by squaring the components, but you know, 9. You can just find this magnitude of the vector, and you can tell what it actually would be in a way. So that would be 81 plus 16, 97. Just for say, oh, here, they're above here. We can just dot any of these vectors. You could dot any one of these vectors. You can tell that this would be 9 cosine t sine t and -9 cosine t sine t, and that's 0, and that's going to be 0. So dot any corresponding vectors, and you realize that they're mutually perpendicular vectors. They're also mutually perpendicular unit vectors because all these vectors have a magnitude of 1. Also questions? All right, that's enough warm up for now. Oh, so you say object. It's okay to object.
Stretch.
So 2.4 brings things into perspective, okay? This just goes back to the idea of curvature and like, why is it so important? You'll see. This is re-expressing the curve in its arc length parameter, hence curvature is magnitude of R2 prime S. And this is to reiterate that if we do so, we simply, you can tell I just got really tired of doing this by hand. And in Maple, we'll just define the curve, take the first derivative, take its magnitude, second derivative is magnitude, and hence the curvature is 27 divided by 106, because this curve was initially expressed in terms of its arc length parameter, a potential exam problem. I mean, you know, sometimes give you some light problems and you just know if it's in terms of S, it's just magnitude of R2 prime S, correct? All right, here we are. Let's learn the vector approach that's not in your textbook. We can take into account what are called the components of acceleration and what they represent. And if you follow along, let's just take a look at T and N only. Yep. And the fact that if I take along the second derivative of R, it's acceleration, correct? Acceleration points in a direction of concavity. And so does the principal unit normal vector. We have to assume that the acceleration vector is not orthogonal to T because it's not always is. Then if I take the acceleration vector and project it onto T and also project it onto N, vector projections from chapter 1, right? The projection forms a vector along T, but it also forms this right triangle. You remember from projections, we talked about the vector, the orthogonal complements. Okay, it's a lot of information I'm pulling forward, I understand. But the reality is, if I project A onto T, the length of that vector, which is the base of this right triangle, is called A sub T, a scalar. It is defined the tangential component of acceleration. I project A onto the principal unit normal vector, it forms another base of the right triangle, defined A sub N, defined the normal component of acceleration. Using, and I'll not say basic anymore, vector sum. It wasn't as simple as it seemed when you took your exam. The vector sum with a check mark here says, if I sum two vectors, right? These two vectors particularly, the sum would be the resultant, which is A, correct? The vector component of T along this projection is in fact the length a sub t with the vector t. A sub t, t, plus a sub n, n gives us this first equation. Thoughts? This equation is going to save you a lot of points on your next exam. So once again, any thoughts?
Thank goodness for Pythagoras.
Yeah. According to Pythagoras, we could take any of the right triangles and just say the magnitude of a sub t squared, which is just the hypotenuse squared, right? Plus a sub t squared is equal to a sub t squared plus a sub n squared. So what we have is a vector equation and a scalar equation. One is vector sum and the other is Pythagorean theorem. What we'll learn, and I won't do this other vector proof because it'll be a bit too time consuming. What we do know for projections though, if I project A onto T, by definition, I'll write the lengthy definition of that. If you recall the projection formula, it's A dot T over its magnitude. But, we're not looking at the direction, just the projection, the scalar component. What's the magnitude of big T? 1. Hence, if that's equal to 1, then the projection is A dot T. Good? And we can say the same for the projection of A onto N. Okay? So please keep these two in mind and I'll show you where this leads. We have a linear equation. I'm going to add something here. So we have acceleration is equal to a sub t, tangential component, times t. And then we have a sub n, normal component. A sub n times n, right? We have the fact that a sub t is equal to, from the projection formula, just a dot t. Acceleration dotted with unit tangent. Well, acceleration, let's just write in layman's terms, well, in your terms, is just r2 prime t, isn't it? And what's the formula for the unit tangent vector? Beautiful, you just created a formula for a sub t. Dot, yes. This lengthy proof shows that a sub n, I want you to read this proof, by the way, that a sub n can be found using that formula. Cross. I'm going to revisit that problem we did when we took the derivative of big T of t. Can anyone tell me what that vector was? And we're going to apply this concept quickly.
Is that A and N supposed to be brought out?
Cross. Yes. So one is dot and one is cross.
You have it as
Where's
A n equals.
no. A sub n is a dot.
Okay.
It's a dot n, but the proof led to this. It's a very rigorous proof. So I want you guys to go back and read it at some point and post this PDF. What was R of t for that problem that we did where we had to take the derivative of big T of t? It was like t and what was the first term? Sorry.
T,
Second term.
2/3 t to the 3/2.
And then
T.
okay. So what I've done with this approach, which I've always taught in Calc 3, reduce this concept to a simple linear equation. We find the first derivative, which was 1, t to the half, if I recall, and 1, correct? Really, a student that would prefer to find the rigorous derivatives, and that's quite fine. I will not be upset with you. Second derivative is going to be 0, correct? 1/2, t to the negative 1/2, and 0, right? Keep in mind, the second derivative is in fact acceleration. So we have already checked off that. That's done, right? What you realize there, you'll only have a single unknown, which is n. And we can just solve the equation to find n. And once you have n and t, you can cross them to find b. So we have time just to find n. So if we have a, let's find big T. And we found big T, which was in fact that vector divided by its magnitude, right? From the last, the magnitude of r prime t was in fact the root of 2 plus t. Is that what we got before? Fair enough. And then all I need to do is find a sub t. A sub t but the formula for a sub t is r2 prime t dot r prime t divided by its magnitude. I wrote the magnitude in the denominator. When I dot these two, what do I get? It's gonna be beautiful. 1 times 0 is 0, 0. And what is t to the 1/2 times 1/2 t to the negative 1/2? Good, because 1/2 minus 1/2 is 0 for the exponents. Very good.
Yeah.
We're good? So a sub t is 1 over 2 root of t plus 2. Go back to my equation. Check. Check. And all I need to find is a sub n. A sub n requires the cross product of these two vectors. Oh, I have zeros. That's going to be beautiful. A sub n, I'm just going to do I, j, k. And what was that? 1 t to the 1/2 and 1 0. What was that? 2t to the negative 1/2 and 0, correct? Or 1/2, thank you. And divided by root of 2 plus t. And we're going to take the magnitude of this answer when we're done. So a sub n would give us the magnitude of some vector. So it's going to be 0. It's going to be minus 1/2 t to the negative 1/2, comma. Middle term is going to be 0. And that term is going to be 1/2 t to the negative 1/2. When I take the magnitude of that vector, it's going to be the square root of these squared. This will be 1/4. I think it was 1/4 t plus 1/4 t. Is that correct? Divided by the root of 2 plus t. So a sub n. What is 1/4 t plus 1/4 t? Half of t. So root of 1/2 t. Our time is up, but at this point we've found all the unknowns. Good. Plug them into the equation and try to solve that linear equation, and that gives you n without finding the derivative. We'll do much more of this on Friday because we're really at the close. Good. So do know that we've found all the unknowns. What I'd like for you to do just to complete this exercise so we can compare results is just solve that linear equation. Just subtract, add, divide where necessary. Does everyone see that? Yes.
Should be, it can be negative.
Where's that? For which one?
Numerator,
To negative,
1.
why is it negative one? Well, what I,
Because it's -1/2.
didn't that square some terms? I'm trying, what am I missing?
You got t to the -1/2 times t to the -1/2.
Oh, sorry, -1, here.
Yeah.
Yes,
Yes.
thank you. Yes, that would have made a difference. Thank you. Here goes Ethan again. And that, I think that would just be 1 over, this 2 just dropped to the bottom, so it's got 2t plus t squared. Just finish that up and we can compare answers on Friday. Thank you for your time. And let me know if the upload works for everyone. All right, have a good rest of the day. Did Alicia show up? Samson?
No,
No, she did not. All right, thank you so much.
no, neither did Leo.
Oh, neither did you. Interesting. This is not a good day to miss.
Well, I was here.
Yes, thank you, Professor Havas.
Listen, I gotta run to trade class. I'll talk to you later.
All right, thank you. See you.
Bye.
Bye.